Okay, hi everybody. So we are continuing the Grand-Canonical ensemble presentation. What we have found so far is that for the Grand-Canonical ensemble, wait a second, is this on? So for the Grand-Canonical ensemble, the partition function is of the form z equals to the sum of I, okay, e to the naught minus beta, ei minus ni multiplied by, or minus mu multiplied by ni. So what is ei? Ei is the energy of state number I. What is ni? Ni is the number of particles at state number I. Now, for Grand-Canonical ensemble, I remind you that the state is identified with two quantities. Energy of the state, okay, and the second quantity is the number of particles for the specific state. But the moment that we know those quantities, and we know what is ei, we know what is ni, and we sum up over all the states, we know the partition function and the relation to other physical quantities were provided to us by the Grand-Canonical potential, okay? Or we can do always the other way around. If we know z, okay, if we know the partition function, the probability to be in a given state, okay, the probability to be in state I is provided to us by e to the power minus beta ei minus mu ni divided by z. Okay? So either we go to the Grand-Canonical potential, which is a Legendre transformation of regular energy, or we calculate the probabilities, and we use those probabilities in order to calculate whatever we want. Average energy, average number of particles, average entropy, not average, just that entropy, etc., etc., etc. Everything is calculable from those quantities over here. Now we are going to some examples where this specific formalism is actually very, very helpful, and those examples are of quantum gases. Okay. Why it's called quantum? Well, we starting now already we will see that we must take advantage of the nature of the particles. Either they are fermions or the bosons. We already have seen, okay, that we need to take the nature of the quantum nature into account. Remember the Gibbs paradox, because it was actually the quantum nature of the particles which contributed to this correction of dividing everything by 1 over n factorial. Why gases? Well, gas, at least from our perspective, is a system of particles that are not interacting. Okay? So we are going to assume that we are looking on a set of quantum particles that are not interacting. There are going to be a set of states, but at least, you know, the simplest case is where the particles are not interacting. This is not exactly true. We will see this. Okay, we will have some sort of effective interactions between the particles, but generally the easiest cases are when the particles are not interacting. So the first example is a little bit of a made-up example. We are looking on fermions. Okay, remember electrons, for example, are fermions. And the property of a fermion is that each quantum state can be occupied only by one single particle. It's impossible, it's an outcome of a symmetry, or actually anti-symmetry of a wave function, a solution to a Schrödinger equation. But fermion is a particle, or two fermions cannot be in exactly the same quantum state. Now here we have the system which we made up have three different energies: E1, E2, and E3. Okay? Now those systems are simply made up in order to illustrate the properties of the Grand-Canonical ensemble. So if we are looking on fermions, each state now can be either occupied by a fermion or unoccupied by a fermion. But this is also not exactly true. Why? Because fermions, and specifically I'm using the word electrons, have also something which is spin, right? So a spin of a fermion or an electron can be 1/2 up or minus 1/2. And those are two different quantum states. Now, the spin introduces degeneracy. Okay? What do I mean by that? Spin, if we do not have some external magnetic field, spin is not actually contributing anything to the energy. It's contributing to the angular momentum, but it's not contributing anything to the energy as long as we do not have external magnetic field. So we can actually say that we have two substates for each energy. Okay? One state is with spin 1/2. One state is with spin minus 1/2, but it's exactly the same energy. Okay? So I'm drawing it here as two different states, but they are associated with exactly the same energy. So here, 1/2, minus 1/2, 1/2, minus 1/2, 1/2, and minus 1/2. Okay? Now, what is actually the problem here to use canonical ensemble? The problem is that the moment I put a particle over here, okay, it affects immediately everything else. It immediately states that this box is filled, and I cannot enter or introduce another particle into this state. So different particles are effectively interacting with each other. Okay? Although I'm using word gases and they do not interact, but because they are fermions, the moment that this state is occupied, okay, this effective interaction between different electron states, no other electron can be with energy epsilon 1 and spin 1/2. Why? Well, because Pauli do not allow us to do so. Right? Now, so we're talking about gases, we're talking about non-interacting particles, but because they are quantum particles, everybody are interacting. This is the meaning of quantum gas. Okay? There is no interaction, direct interaction, but quantum properties are making everything interact with each other. So for canonical ensemble, we cannot use it over here. Why? Or at least it's going to be hard, because there is interaction between different particles. Okay? And it's hard. We already have seen in the bi-model, in the black body radiation, we can solve problems with interactions, but it's hard. Okay? The only thing that we actually can solve are non-interacting particles. How Grand-Canonical ensemble is going to help us? Now, the difference, some sort of a small difference, but it's actually not so small, is when you're looking on canonical ensemble, we're thinking about particles. Okay? And particles dictate what is the total energy. And we factorize over different particles. Okay? Remember what we have done in the bi-model. In the bi-model, all those vibrations were coordinated somehow, and we found a new way to look on the same system as if they were not coordinated and they were independent. Okay? Here there is no way to do this. Why? Because this particle, when it's sitting in this specific position, it's always affecting everybody else. Okay? There is no way to get out of this. Now, Grand-Canonical ensemble provide us a path through. So what is the thing that Grand-Canonical ensemble permits us to do? We can look on the system not as a sum of different particles, but you can say the summation here is over states. Now, if all those states are somehow independent, okay, and we just only need to count on the different states and not the different particles that are occupying the different states, we're also good. Why? Because as long as the states are independent, we can make the Z a factorizable property. Okay? So what I'm saying is as follows. Let's try and write down this function, this partition function for our system. Okay? So what we have, Z is as follows. So we sum up over all different states of the system, e to the minus beta e I minus n mu I. Okay. I'm sorry, mu n I. Mu n I. Now, what is the state of the system? So a given state of the system is, well, I have no particles with epsilon 1 and spin minus 1/2. I have one particle, okay, at state with epsilon 1 and spin 1/2. I have no particles at state epsilon 2, and I have no particles at state epsilon 3. Okay? So this is a given state. So we can say, well, there is E, I don't know, K, for which the total energy is epsilon 1, okay, and N for the specific state K, okay, is going to be 1. I can also have E, I can say it K prime, some other state, where the total energy is going to be epsilon, okay, and the number of particles is also, and K prime is also 1. What is the state corresponds to? Okay, yep, when I erase this position over here, and I put this particle in the degenerate state. So the spin is actually adding up to the degeneracy of the states, because it seems like exactly the same state, K prime and K, okay, but they are different because I put my particle with a different spin. Okay, so I have to go over all these different possible states of the system, and which looks like really tiresome, because I can have state like this and a state with 3 particles over here, right? And this state is going to be to describe, it's a state of K prime prime, for example. So the total energy is epsilon 1, one particle here, epsilon 2, so it's epsilon 1 plus epsilon 2 plus epsilon 3, okay? So it's epsilon 1 plus epsilon 2 plus epsilon 3. This is the total energy of this state, and the number of particles in this state, and K prime prime, is 3. Okay? So what I need to do in order to compute this sum over here, I have to consider all the different states for the system, and there is very many of them, extremely too many. So what do we do? Okay, so remember, we hate combinatorics, or at least I do, and we don't want to go over all the different states. The only thing that we want to do is to perform some sort of a exchange of the representation in order to look on this guy and say, well, it's actually factorization, and for canonical ensemble it was factorization over different particles. Okay, and here we're going to say it's actually a factorization over different states. Okay? Let's see exactly what I mean. Yeah.
Do you want to account for all possibilities for all number of particles?
Yes.
Until the energy is...
Yes. So it goes from a situation where I have absolutely no particles anywhere, okay, till 6, till everything is absolutely filled. All the different possibilities. Okay, this is what I want to actually count. It's a tiresome problem, especially here there are only 3 states, 6 states. Consider if we have, you know, an Avogadro number of states. Come on, it's no use of trying to do this combinatorics again and again and again. There is some other technique, and this factorization that we've seen for canonical ensemble is going to appear again. Okay, let's see what actually happens. So we have this summation over I, E minus beta EI minus NI mu. Okay. Now, I want to write this down, sum of AI, e to the power minus beta. Okay. And look what we have here. So, the energy, it's always the sum over all the different energies for each state. Okay? I'm looking up on the total energy is how many particles are at energy epsilon 1, how many particles there are in energy epsilon 2, and how many particles there are in energy epsilon 3. Now, the total number of particles at epsilon 1 is, let's forget about the degeneracy. Let's assume that we are only looking on particles with spin 1/2. So I can say there are, let's put it, n prime particles at state with epsilon 1, okay? And there are n2 prime particles at state epsilon 2, okay? And there are n3 prime particles at state epsilon 3. Okay, minus what is n1 can be if I'm looking only on particles with spin 1/2. So it's either 0 or 1, right? n2 prime is also either 0 or 1. So it is saying how many particles are sitting over here. It can be either 0 or 1, right? The same goes for this guy. It's either 0 or 1. Okay. Now here is minus something multiplied by mu. Okay, what is this something? Ni is the total number of particles. Okay, the total number of particles here and here and here. I can go over here and say this is going to be n1 prime plus n2 prime plus n3 prime, right? Now, this is a little bit tiresome because I forgot about the index I. Okay, so let's put it over here. I, and I. What is, and I'm going to write it down, n, I, okay, prime 1, the number of particles at energy epsilon 1 for state I. Okay, so this guy is actually a multiplication of what? So we have sigma of I e minus beta, okay, of ni 1 prime epsilon 1 minus ni, okay, 2 prime epsilon mu multiplied by e to the power minus beta ni 2 prime epsilon 2 minus ni 2 prime mu multiplied by e to the power minus beta n I 3 prime epsilon 3 minus n I 3 prime mu. Okay? Because it's a summation inside the exponential is just a simple multiplication. Okay? Now I'm going and summing up over all different n1 prime, n2 prime, n2 prime, n2 prime, n3 prime, and n3 prime. Okay? And they're completely independent of each other. They're completely independent of each other, and I know that, I'm sorry, this is 1. Okay? And I know that this guy and that guy are there exactly the same. They're exactly the same. So this guy is going to contribute to me, okay, 1 plus, or let's write it down. So this guy, it's either e to the power minus beta, 0 multiplied by epsilon 1 minus 0 multiplied by mu, or it is e to the power minus beta epsilon 1 minus mu. The same goes for this guy. It is either e to the power minus beta 0 epsilon 2 minus 0 mu, or it is e to the power minus beta epsilon 2 minus mu. Again, we can do this trick once more. So it is e to the power minus beta epsilon 3 minus epsilon 0 mu, or it is e to the power minus beta epsilon 3 minus mu. Now the different numbers are completely independent of each other. Why? Because the occupation number on ny prime I is the total number of particles that can sit over here. Okay? It's completely independent of the total number of particles that actually now sitting over here. How I treated the interaction, I said that I restricted the total number of particles to be either 0 or 1. Okay? So what I have done is basically saying they are interacting, but if we count all the different states and we doing it not for the different particles but for the different states, and we use this quantum restriction that basically says the number of particles is restricted to be 0, 1, okay? We can say that this part is independent of this part and independent of this part. So when I sum over all the different states, I'm basically saying I'm summing over all the different appearances of n1 prime, over all the different appearances of n2 prime, and all the different appearances of n3 prime. And those three numbers, quantum numbers, are independent of each other. Okay, so what is Z? Z is this guy plus this guy. So this is 1 plus e to the power minus beta epsilon 1 minus mu. Now this guy contributes me again 1 plus something else. So it's 1 plus e to the power minus beta epsilon 2 minus mu. This guy contributes what? 1 plus e to the power minus beta epsilon 3 minus mu. Okay? So you see, I've managed to sum up over all the different possibilities, okay, fairly easy by saying I factorized. I factorized everything, but I haven't used particles in order to perform my factorization. I used states. I said this state is independent of that state, is independent of the third state. What exactly is independent? The occupation numbers. The number of particles per state. This is quantity that's independent. Okay? And I sum over all of those quantities, those occupation fractions, and this is what I obtain. Okay? So this is Z. Now, I still need to perform one small correction. And what is the correction over here? Exactly. So I used a system where I killed the -1/2 spin. Okay? Over here, over there, and exactly over here. Now again, those occupations are independent, but they produce exactly the same answer. Okay? So because of the degeneracy of my system, I have to put over here 2, 2, and 2. Right? This is simply because the system is degenerate, and the contribution of occupation of this state and occupation of that state give me exactly the same, and it has exactly the same energy. So this is introduced the degeneracy factor of 2. Okay. Now that I have this, This is my this is Z, okay? This is Z. I can go and compute what? I can go and compute the probabilities to be in a given state. In any given state, okay? What is the probability to be in a specific state, okay? Now, what the states are. So for example, what is the probability to be in a state, okay, in a given specific state? It is always Fi, it is e to the power minus beta epsilon ei minus mu ni divided by the partition function z. This is the general result. So if I want to answer the question, what is the probability to find one particle in state E3, epsilon 3, with spin up, one particle in state E epsilon 2 with spin minus 1/2, and one particle in state, or no particles with state epsilon 1. So this specific, let's call it K, Fk, is e to the power minus beta. So we're saying we have one particle in epsilon 3, one particle in epsilon 2, okay, minus mu multiplied the total number of particles, 2 divided by this z over there, okay? But this is still cumbersome because it is actually not an interesting question to say what is the occupation fraction, or what is the probability to see this particle over here, that particle over there. I want to ask slightly different question. I want to ask what is the probability to see this state occupied. Why it's interesting? It's interesting because we factorized over the different states. Remember, so the partition function is a multiplication of the partition functions of every given state. Okay? As in canonical ensemble, where at some point we realized that the partition function, okay, is a multiplication over many different partition functions of the different particles, and if I actually can look on the partition function of a single particle and say what is the probability of this particle being there or here, the same I can answer for the system. I don't want to answer the question what is the probability to see a very specific configuration. I want to answer a question what is the probability of state with energy epsilon 1 and spin 1/2 to be occupied. Okay? Since I made this factorization, I can say I don't care about the general configuration. I can look on the occupations of the different states that are composing this big system. Okay? And the answer is very simple. Why it's simple? Because, look, the moment I have factorization for the total energy, okay, I can say I can look only on one specific particle, and we have Z1, Z2, and Z3. What is Z1? Z1 is the Z1 1/2. Let's call it like this. Z1 1/2 and Z1 3 1/2. What is Z1 1/2? Is the partition function of what system? Of a system that has energy epsilon 1 and spin 1/2. Okay? I don't care about everybody else because I factorized over all the different states. Now Z1 1/2, I can look and I can say this is my partition function of this subsystem. It's simply 1 plus e to the power minus beta epsilon 1 minus mu. If I wanted to look on the second state, okay, with spin 1/2, it is going to be 1 plus e to the power minus beta epsilon 2 minus mu. If I want to look on the third state or third energy, I can say this is simply 1 plus e to the power minus beta epsilon 3 minus mu. If I wanted to look on the partition function of the energy epsilon 1 and spin minus 1/2, it's going to be exactly equal to z1 1/2. The same goes for z2 1/2, and the same goes for z3 1/2. So I can put a plus minus over here, okay, and write down that the total partition function is z 1/2 multiplied by z1 minus 1/2 multiplied by z2 1/2 multiplied by z2 minus 1/2 multiplied by z3 1/2 multiplied by z4 minus 1/2. Okay? Z4, why I have Z4? I don't know. How it helps me to answer this question, what is the probability of a given energy? Okay, to find a particle with a given energy and spin 1/2. Okay, so what it is, so the probability to find a particle with a given energy, okay, with a given energy and a given spin is what? Is the sum over all the different probabilities for all the different states for which my given particle is sitting in a specific position, in a specific state, and I sum up over all the different occurrences for all the other particles or all the other states. And eventually, if I call it f epsilon 1, okay, so f 1/2 epsilon 1, so what is this? This is the probability to be, for a state, for an energy epsilon 1 to be occupied with a particle with spin 1/2. It is going to be what? It is going to be e to the power minus beta epsilon 1 minus mu divided by z 1/2. Okay, where I got it from? I got it from a general expression. Okay, my general expression was I sum up over all the different particles, and I sum different states for which the contribution of states epsilon 1 is going to be this, and I always divide it by the total z. Okay, I divide it by the total z1, z2, z3, z4, etc., 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 etc. Okay, so basically it is a summation of the following form. It is a sum over all different states where I have e minus beta epsilon 1 minus mu plus n2 prime epsilon 2 plus ni 3 prime epsilon 3 minus ni 2 prime plus n3 prime multiplied by mu divided by z1 1/2, z2 minus 1/2, 1, z2 1/2, z2 minus 1/2, z3 1/2 multiplied by z3 minus 1/2. Okay, I sum up over all the different occupation fractions of n2 prime and n3 prime. Okay, this guy I don't sum over all the different occurrences. It doesn't matter. Okay? So eventually, after I sum over everything, okay, I'm left with this guy over here, e to the power minus beta, epsilon 1 minus mu, because I can take it out of the parenthesis. Okay? And here I have a sum over I divided by z 1/2 1, e to the power minus beta n2I prime epsilon 2 plus n2I prime epsilon 3 minus n2I prime plus n3I prime mu, okay, divided by all these z's that I have. z1 minus 1/2, z2 1/2, z2 minus 1/2, z3 1/2, z3 minus 1/2, and all of this summation is exactly 1. Okay? This is simply 1. So this is the result that I obtained over here. Now, if you remember, this is the outcome of factorization. The moment that our partition function is a multiplication of different partition functions of different states, I can treat each of those states as completely separate of everybody else and say this is the partition function of a given state. And the same way I treat a partition function for a big system, I'm going to treat the partition function of a small system. What is the probability for a given state in a big system? Is this a prefactor given by Grand-Canonical ensemble divided the partition function. If I have a small system now, and this is a mathematical result, okay, if I have a small system, I write down this prefactor of a given state divided by the total partition function. That's it. Okay, so this is where we stand. We basically factorized, but we factorized not over different particles. Particles are dependent. We cannot break this quantum mechanical, very strong quantum mechanical rule. But the different states are independent, and we can represent the partition function as multiplications of the partition functions of different states. And the partition functions of any given state is described exactly by this Grand-Canonical ensemble. Okay? All right, so if we know what is going to be the average number, okay, of particles that are occupying N1, N1 is the average number of particles with energy epsilon 1 and spin 1/2. So N1 average is F epsilon 1 1/2 multiplied by 1, right? So what is this epsilon 1 multiplied by 1? The probability that I have one particle sitting at energy epsilon 1, okay, with spin 1/2, plus the probability that I have no particles sitting at energy epsilon 1 and spin 1/2 multiplied by 0. Okay? So the probability to have one particle plus a probability to have 0 particles multiplied by the number of particles. Okay, so N1 is simply e to the power minus beta epsilon 1 minus mu, okay, divided by what? Divided by this Z1, which is simply 1 plus e to the power minus beta epsilon 1 minus mu. So this is N1. Now, if I want to calculate the average number of particles in the whole system, so N, average, so it is simply N1/2 plus N2 plus N3 multiplied by 2. Why 2? Because I have spin 1/2 and spin minus 1/2. So I have 2, 2, and 2 everywhere. So the average N is going to be, I'm using this formula over here, is 2 epsilon minus beta epsilon 1 minus mu divided by 1 plus e to the power minus beta epsilon 1 minus mu plus 2 e to the power minus beta epsilon 2 minus mu divided by 1 plus e to the power minus beta epsilon 2 minus mu plus 2 e to the power minus beta epsilon 3 minus mu divided by 1 plus e to the power minus beta epsilon 3 minus mu. Okay. This quantity over here is the occupation probability. Okay. And N over here, which is written, is occupation fraction, because the occupation fraction is the average quantity of particles per state. Now, why it's occupation fraction? It can be have a maximal value of 1, because they are not allowed more than 1 particle per given state, and minimal value of 0. Okay? The occupation fraction says to us what is the probability of a state to be occupied in some sense, right? Because N1 average is exactly F epsilon 1, because the other contribution over here is multiplied by 0 and we don't care about it. Okay? So if we want to explore what is the probability to see particle in a given state or in a given energy, we had to study this guy over here. How much time do I have left? 2 minutes. 2 minutes. All right. So I will just almost finish here. I just want to say something about this occupation fraction. So what we are going to do next week, we're going to study in detail the behavior of this occupation fraction. Okay? But if we look on the behavior over here, okay, and we look of N1 average as a function of epsilon, okay, as a function of epsilon, and what is N epsilon? N epsilon is e to the power minus beta epsilon minus mu divided by 1 plus e to the power minus beta epsilon minus mu. This is the probability to see particle in energy epsilon and spin 1/2 or minus 1/2. And in general, it goes, if the energy is very small, okay, if the energy is very small, all of this goes to some specific value over here. And this value over here is simply e to the power minus or beta mu divided by 1 plus e to the power beta mu. Okay? So we start over here. And when the energy is very, very, very large, okay, where this guy goes to, when the energy is extremely large, 0. Okay? So this guy eventually goes more properly. It somehow decays towards 0. So this is the occupation fraction for some specific temperature. What we're going to see that the properties of this function, it's sometimes also called a sigmoid function, are very interesting, and they sometimes will dictate to us behaviors of fermions. Okay, occupation behaviors of fermions, conductions of electrons in metals, they're all going to be described by the sigmoid function. And we're going to explore how this function behaves if we have different temperatures, if we have different chemical potentials, and etc., etc. It's actually a really neat behavior because we will see that we basically have two limits. One limit, which is not so interesting, when all this function is extremely broad and spread out. So basically the particle can have any energy. The probability almost the same everywhere. But we will see instances when this behavior is going to look like this, almost a step function. Okay? So for specific temperatures, or low enough temperatures, and here it's something is around you, we will see that there is a probability that that the specific state is occupied is exactly 1, okay? And for energies above mu, the probability drops exactly to 0. We will see why this is important, especially in properties of conduction, and etc., etc. So I will see you next week.